All right, so today we're going to do a force table experiment to show you how to use the force table, set it up, and then set up your calculations so that you can calculate the resultant and the equilibrant vector where you want to place that to set your forces in equilibrium. All right, so the first thing, our tables are not level. So you will have to make sure that your force table is balanced before you can start your experiment. So whatever you have to do to lift the legs up to get your balance to center itself, you should set that up before you start. You will then position your pulleys onto the framework. I'm going to set up 2 for mine initially so that we can see how the movement will happen in the net direction of where the resultant vector will be. So your pulleys are sided, and you want to make sure you have the correct side up there. So you can see that the pulley has a little divot in there, and I can line that up exactly with the degrees. And so you can see this pulley is lined up right at 0 degrees. Let me move this out of the way a little further. There we go. And so the second pulley that I have over here also is set so that the pulley is showing where that little divot will form. I have it set right now at 135 degrees. So we're going to start there, right? When you're setting up your ring system, you're going to tie the hangers onto the center ring. So I'm going to go ahead and do that and get that set up and set the string so that they'll hang over the pulley system. All right, so I have the pulley system set up now. I don't have any weights on there yet, but you can see that the pulley is set up so that there's room for my weight to actually pull down on this system, right? And you can also see that there is a center screw on your force table. You can reach that at the bottom there, and you can move that up and down. And so because the pulley system and the weights that are hanging off of it, right, are set up so that they're not equivalent or directly opposing each other, you're going to have a net force on this system, right? So if I move this screw down, right, my ring, right, is going to want to move in that direction of the resultant force, right? The net force on the system is going to pull the system right in that direction. So I have an idea already about where my resultant force is going to end up based on how it's moving, based on how it's moving with this ring system. All right, so now I'm going to add some weights to either side, and I will tell you those weights so that we can work a problem and calculate our resultant vector. Okay, so with the weights set up, you can see that there is a definite pull to my center, right? If I'm letting this go, it wants to pull kind of off into this direction, which makes sense because I have more weight over there. So one more consideration before you totally start your experiment, you want to make sure that the pulleys are pretty straight. So you can see I have a little bit of an angle on my system. I'm going to try to get that down into just a horizontal plane. All right, so I've moved my pulleys a little bit, and now you can see it's less angled. There's still maybe a little bit of an angle, but this is pretty close. So I want to make sure that my ring is not touching the force table, that it's suspended fully above the force table and in as straight a line as I can possibly get. I may just adjust this first pulley just a hair more as it's still angled upward. All right, so there's my final positioning. My force table is completely set up now, and I've got my weights on there. So when we're thinking about the forces at each position, right, I only have 2 forces that are being involved at each of my weight positions, right? So on this side, you can see my weight force, right, is going to be going down, right? And weight is mass times gravity. right? And then you have a tension force going up on this system as well that's going off around the pulley and then to the ring. You have the same thing on the other side. This pulley is weighted a little higher, but you can still see it's free floating, and it has its weight force going down and the tension force going up. We are saying that friction in this case is negligible, and we are ignoring the mass of the ring as well and saying that that's negligible on our system. Okay, so here's our setup. Now we need to do our calculations to figure out where the resultant vector is, and then how we calculate the equilibrant vector, which is going to make our system balanced, right, and at equilibrium, right? So we know this is currently pulling off into this direction, right? If I release it, it wants to go there. It doesn't want to stay centered. So the resultant, or the net force on my system currently, is pointing off in this direction somewhere. The equilibrant force that I'm going to need to balance the system will have to come off of this side of the ring somewhere, and you in your first experiment will do this experimentally, right? So kind of see, where do I need to pull on my ring to get it over in this position? That's where I would want to put a third pulley system to try to get that equilibrant vector to show up. All right, so now we're going to do some calculations and how we can actually use either vector addition, so geometry, or our component breakdown and use trigonometry to calculate that resultant vector. Okay, so this is, again, looking at your trial 2. So in your trial 1, you were experimentally finding your equilibrant angle. So in this trial, you're doing a prediction first. So remember, we just loaded up the two forces onto our force table, and we can see that if I didn't have the screw up in the middle, that my ring would kind of shoot off the table in the direction of the resultant vector, right? So I've just filled in my table now for that. Again, the mass that I'm using for the first force is 115 grams. So I've converted that into the forces, which is 1.13 for mine. Remember, it's mg because your mass is hanging down. And so you've got the weight force that is being added at each position on your force table. So we can use mg as our weight. And remember, make sure that you convert your mass into kilograms in this experiment, right? Because your masses are all given in grams. So that's an important component. So for this next section, you are going to be using the head to tail method of building your vector. And this is actually just going to use literally a ruler and a protractor to measure your angles that result to calculate your resultant vector. So I'm just going to draw onto, hopefully I can do this on my iPad. You can draw an X and a Y axis onto your graph paper. Maybe. Whoop, sorry, mine is not completely straight. Yours will look better because you'll have an actual piece of paper that you're working off of and not trying to do this on an iPad, which enhances the difficulty. Okay, so you can label your y-axis and your x-axis. And for mine, since my values are a little high, I am going to say 0.2 centimeters. Or sorry, 0.2 newtons equals 1 centimeter. That's the scale that I'm going to use, right? And so my force in the x direction, right? X on the force table is 0 degrees. And then as we rotate around, you've got the 90-degree position over here, right? So we got 90 degrees, 180 degrees, and 270 down at the bottom, right? And if we went all the way around, you go 360 and back to 0. Okay, so that is our directions. So the first force that I have on the table is the 115 grams that are hanging off of the 0 position, right? And if we look back up at my table, this is equivalent to 1.13 newtons of force, right? So if I use my conversion to convert this into centimeters, 1.13 newtons, and I'm going to say that each 0.2 newtons is worth 1 centimeter for 0.2 newtons. This is going to give me the total centimeters that I need to draw on my x-axis. Okay, so if I calculate that out, that's telling me that my force of 1.13 newtons should be 5.65 centimeters in length. And I just went ahead and calculated that also for the second force, which was 0.74 newtons, and that was equivalent to 3.7 centimeters. So we just need to draw those then physically on our diagram. So I'm going to change the color so you can see the forces. All right, so we shifted my forces to blue. And my first force is the 115 gram one. It's hanging off of the 0 position. And I said that should be 5.65, right, centimeters away. So I'm just going to try to draw that on top here. Again, you won't be drawing on top of your iPad, and your forces will probably look nicer than mine. So I'm just going to draw that in there, right? And that's my initial force there, right? All right, so that is force 1, right, in geometric component. And then my second force is not straight on, so it's a little more difficult, right? So my second force is at an angle of 135 degrees. So I need my protractor for that, right? So if I set my protractor down at my 0 point and I guide it over to 130, that is going to be over here on my diagram. And so I'm just going to make a mark at 130. So I know the direction from center that my force should go over there. And I know it needs to be 3.7 centimeters long. So again, I'm just going to measure that vector over here. Sorry, it's kind of ugly and not exact and precise. Yours, again, should be better than mine. Okay, but you can see the lengths of the force reflect the force magnitude, right? And then I've also tried to draw the correct angles over here, right? So this angle in between these two is at the 135 mark, right? I'm just going to erase that off, maybe. Okay, all right, so in the head to tail vector model, right, we said that we're going to place the vectors head to tail, and that is going to give me the region where they're going to create the resultant vector, right? So you can do it either way. I can choose to take the vector that's along the x-axis and move it up to the head of the other vector and draw it in here, or I can take this one, right, and I can draw it over here. They both should point to the same spot. And then you're going to draw the resultant vector from your origin to wherever the head of the last vector ends up. So I'm going to take maybe my x vector and I'll draw it up at the top. So I'm going to change the color for that as well and just use orange, I guess. And I'm going to keep the same length for that vector, which is 5.65 centimeters. And I'm going to try to keep it on that horizontal, right? So I'm going to draw this guy out, head to tail, to about 5.65. Okay, again, yours can be more exact. It's weird working on this iPad in this fashion. Okay, so that is adding, right, my x component to the second force, or force 1 to force 2, right? And so this is going to give me that resultant vector. The resultant vector, again, is the net force on the system. I mean, it doesn't like really exist in there, but we're going to draw that on our diagram. Oh, what color should we use for our resultant? How about purple? I like purple. Okay, so I'm going to draw in the resultant vector, and you can see it's going to have a specific length. I'm also going to take the length there. I think that is 4.2. Okay, so I'm going to draw this here. There's my resultant vector, right? And I'm going to say that it is measured by my ruler, that it has a magnitude of 4.2 centimeters. And if I convert that back into newtons, right, we said that there were 0.2 newtons per centimeter. So I have just calculated the magnitude of my resultant as 0.84 newtons. Okay, so I haven't given the direction or the angle, right, that's associated with this degree. So you can physically measure that using the head to tail graphic method by placing the protractor again at the origin. I'm just going to lay that down there. And then I'm going to calculate the theta. Whoop, no, come, oh, geez. Again, you guys will have an easier job of this. So I've lined it up as best I can on my iPad. And I'm going to say it's pretty darn close to 40 degrees, right? So my protractor is not giving me a better detail than that. So I'm going to say theta is 40 over here. So that is this angle that I just measured. And that's the direction. It's going up. So I'm going to say that's the positive 40 degrees right there for that theta angle. So I just calculated based on my graphic measurements that I should put 0.84 newtons of force to the 40 degree mark, and that is where my net force goes, right? So, or that's where that ring wants to go or travel, right? So if I'm looking again at my force table, let's come back over here. So if you're looking again at the force table here, right, where you've got your forces laid out, right, this is telling me that my net force is wanting to go off at that angle of 40 degrees and with a force value of 0.8, what was it, 0.84 newtons. Okay, so that's where the resultant is, or the resultant force. The equilibrant vector that I need to pull off into the other direction to balance this, right, is going to be 180 degrees in the opposite direction, and it's going to have the same magnitude as the resultant vector, your net force vector. So coming back over here in terms of our diagram, right, we just need to add 180 degrees to the other side to get the equilibrant vector, and I'll put that one in orange as well. Right, and it's going to have the same magnitude, which is 4.2 centimeters off in this other direction. I'm going to just keep the straight line because that should give me the 180 twist off to the other side. So this is the equilibrant force, or the E force, right, that I need to predict, right? That's what I was asked to predict. Right? The resultant force is the net force already on the system. That is essentially the net where my ring wants to move with the current two forces that are hanging off of my table. Right? So with this prediction, 40 plus 180, right, is going to just give 220. That makes sense. My downward is at 270, so if this is 220, that means from 0, right? So my angle for my equilibrant, let's use orange. We'll extend all the way around to here. That angle should be 220 degrees. That's where it's telling me to place the equilibrant. We said that that is 0.84 newtons. So I need to calculate back the mass I need to hang off of that side. I will let you guys do that. You should be able to do that. And then you would place your equilibrant onto your force table and see if you can get it to balance and come to rest with the ring perfectly in equilibrium at the center and not shifting and moving about anymore. This is the graphic method for determining the resultant vector or your net force on the system and predicting where the equilibrant is going to be. So you can also do this using components or trigonometric functions to add your vectors together to get the resultant vector. It still takes this head to tail kind of diagramming to get the triangles to show up for you. So we did that in a previous lecture where we showed the angles adding up. Okay, but that only occurs when you actually are adding your vectors together, right? You can't get your triangles to like appear for you if you don't add your components together. So always having one component, I'm just going to come down. You can use the other graph paper to do the component method, right? And for the component method, you don't have to pay attention to how, well, you should still have like longer angles. I'm going to say my x-axis is the 0 on my force diagram. And I always hang one of the forces at the 0 point because then it's going to make my calculations easier. I'll only have to break down one other force into components. I won't have to break down all of them into components, right? So you've got this one that's coming out here. I've already given this one a value of 1.13 newtons. Right, so this force here, I will call this one force A. Okay, so this is force A, 1.13 newtons. We said force B is at 135 degrees, and it is 0.74 newtons. So I'll try to put that in there, 135. And for my diagram, I chose really well. 135 is right along that spine. It's right in between 180 and 90 degrees. And it's going to be less. So I'll draw it a little bit shorter and draw that force component out there. Right? So you've got that force component there. Right? So to break down the component system again where it makes sense, you're going to need to add the vectors back together because you need to get the resultant. And so you need to add the vectors. They can't be added directly, right? Because you've got an angle. They're not in alignment with each other. But I still need to put them head to tail. So I'm just going to move this one that is along the x-axis up. And we'll still keep the x-axis there. I'm just going to move that one into this up position. So I'm going to draw this one again. Okay. So I've drawn my first one connected to the other one, and that's coming into a place where I know my resultant force is going to be, right? So that is our vector diagram. I'm going to erase the first one just to get like more space over there. Okay, so I added my two forces together. That is going to give the resultant vector R, right, off in this direction. So we draw it from the base up to the head. This is R. This top one up here is force A, and the one that's over here is force B, right? That create the resultant vector R, right? So if we are looking at our vector components, right, we know we've got to break them down into X and Y components. The R components, right, if we break them down into X and Y for the R components, they're here and here, right? So this is Rx, and this is ry. Right, so there's your components for the r resultant vector. Right, the a component is in line with our x. Right, so we don't need to break that one down. Right, the ax component equals a in this case. So for force a equals ax, and ay is 0. There's no y component to my force a, which that's beautiful. I don't have to break that one down. My b force, though, I have to break down, right? So my b force is over here. I'm going to change the color for my b force. Okay, I'm just going to draw on top of my b force just so it's a little bit different color. So it shows up, and then the x component of my b force is over here, right? And the y component of my b force is over here, right? So this is by, and this is bx. Okay, so those are my triangles, right? And so I need to break down the components of rx and ry in terms of ax and bx and by and ay. So if we know our angles, right, for our work, right, we can calculate these things. Right, I'm going to go back to blue maybe for showing some of the work. Right, so rx is going to be a combination of ax plus bx, and ry is going to be a combination of ay plus by, right? And then we just have to be careful of the directions that we're going, right? So ax is that whole thing that's over here, and it's represented by the whole force, right? So we know ax is a. So when we're calculating rx, we can leave ax as a. It's the total thing for a, for that force. But bx is not. We have to write bx in terms of the angle, right? So you can use, like, this angle is 135 for me, right? Or you can use this angle here, right? And it should give you the same number when you're using your trig function breakdown. So if I have 135 there, what, 35 more would give me 180? 45 more would give me 180? Okay, so this angle is 45 degrees. This angle is 135 degrees. The only difference that it gives you is the sign, right? So we know the sign for bx, it's moving to the left. It's going to have to be negative for the bx value, right? So I know our equation for bx, it's adjacent, right, over hypotenuse. So I need to use the cosine function for bx is b cosine theta, right? And for by is going to be opposite, and so that is going to be b sine theta. Right, so my distance rx right here, right, needs to be a minus the bx value, right? So the magnitude of bx, regardless of sign. I know that I'm going to have to subtract that off to get the rx. So drawing it out, you need to be able to show, like, what, that value makes sense, that my rx needs to be a, and then you're going to have to subtract off the magnitude of bx. So whichever angle that you use, 135 or 45, you're going to need to make your bx value negative because it's going to the left in the left direction. And you can easily see that you need to subtract it off of the a value so that you can get rx. Okay, so I'm going to do that. Okay, so for mine, when I calculate that out, For the bx component, again, it's moving to the left. So if you use 45 in your cosine, it will give you a positive number, but you just need to note that because it's going to the left, you're going to have to make that number negative. Notice though for by is going up, right? And so up direction is positive. So we will want our sign for that to be positive. So we can go ahead and put these numbers in. And so I put the negative in there, noting that my total value has to be negative. Our formula though is plus in the diagram. And so if you put your negative down here, you're just going to substitute that in. So for Rx, right, this is going to be A, which was 1.13 newtons minus 0.523 newtons. Right? And then for Ry, it is going to be 0 because there's no A component plus the 0.523 newtons from the B vector in the Y direction. All right, so Ry is 0.523 newtons and Rx is something else. Okay, so solving for Rx, we get 0.607 newtons for Rx, and for Ry, we get 0.523 newtons. So once we have these two set up, now we're looking at the R triangle, right? So if we're looking at the R triangle, right, we've got that right angle right there. And so for our R triangle, right, we can use Pythagorean theorem to get the hypotenuse R using our components. So Pythagorean theorem says, in this case, Rx squared plus Ry squared is going to equal R squared, right? Because R is the hypotenuse and X and Y are the sides of the right triangle. Okay, so we can do that math, right? We're going to solve for R. It's just going to be the square root, right, of Rx squared plus Ry squared. Okay, and we just found those values. So we can get our square root of 1.13 newtons squared plus, no, sorry, that's not the correct value for the X component. So we can put in our values. We've got 0.607 for the X component and 0.523 for the Y component. Square both of those and take the square root. Okay, so when we do that calculation, we end up with our R equaling 0.8009 newtons, which that's not too bad from what we calculated, right? Based on just measuring this thing out. We got our resultant at 0.84 newtons. I'm not too sad about that, especially because my geometric measurements were not super accurate, right? Because I was using my tablet and it's difficult to write on. So that's coming out pretty close. Pretty happy with that. All right, so we're not done. We still need to figure out what angle the resultant is going to be at, right? So that is our new theta angle in here, right? We need to figure out this angle. That is our theta, right? Well, we have the sides, right, that we just solved for, so we can use our tangent function in this case, right? So when we have the sides, the adjacent and the opposite, right? SOHCAHTOA, the opposite over the adjacent, is going to equal tangent theta, right? So that is our function that we're using, right? And we know the opposite side is Ry, right? Over Rx is the adjacent, Right, and then we need to take the inverse tangent to isolate our theta angle. So our theta should equal inverse tangent times ry over rx. And we can fill in those values. Rx, 0.607 newtons. Ry, 0.523. Right, and we need to just do the math to solve for the angle. Okay, so we just finished that math up and we figure out that our theta angle has a magnitude, or theta angle is 40.7 degrees and has a magnitude of 0.8009 newtons. You can convert this back to mass because you know it should be mg. Know that you have that in kilograms. You'll need to convert that back to grams. That should give you the weight that you need to post. But we now need to realize that this is the resultant vector, not the equilibrant, right? So that's not going to equalize the forces being balanced in this system. So remember, the equilibrant, right, is equal in magnitude, but it has the opposite angle. So this is not making me happy. Okay, so our theta angle for the equilibrant equals theta for the resultant plus 180, right? So it'll have the same magnitude, 0.8009, as the resultant, but it'll be in the opposite direction to help balance now that net force that's come out of the two forces that we placed onto the force table. So 180 plus 40, what is like 220.7? So the angle that our equilibrant vector should be placed at is at about 220.7 degrees for my example. Right, so if we went back over to the force table, all right, so if we come back and we're looking back at this force table, the resultant vector, it makes sense. This thing is wanting to pull towards the 40-degree mark over here. It makes sense that we are going to want to place the equilibrant vector over at 180 degrees from that with the same magnitude of the net force. And once we do that, you can see that pulling back in this direction is where the equilibrant force is going to need to be added. So you would set up that third pulley over here, and you need to hang the correct mass onto it that you calculate from the force that you calculated, and then see if you can get this ring system to balance in here on your force table. At that end, you should be able to screw the middle screw all the way down flat, and the ring should not pull anywhere. It should stay balanced right in the middle on your force table. Okay, so that is your force diagram for the second one. The third one, you'll have to calculate a mass of unknown value based on how it balances another force. Okay, so that's what your graph should look like.